Hey guys, in this video we're going to be looking at doing something called quadratic regression. And so what we'll want to do is take some quadratic in any form, be it a picture, a graph, a table, what have you, and from that graph, table, picture, whatever, create an equation called the curve of best fit that describes that function. And once we know the equation, now we can bring to bear all the math tools that we have to kind of figure out what's going on with this, to make predictions about values, which is going to be our main focus, and to do all sorts of neat math. So just to give you an example of what this looks like, we're going to take a picture here of a bridge, and you see here in this bridge this nice parabola of the arch on this bridge. And so what we're going to do is just some very basic quadratic regression in order to find the equation of that parabola. So here you can see I'm in Desmos, and I have my equation, which is right here, and I can adjust the values of A, H, and K to change this however I'd like. So the first thing I'm going to do is match the vertex of my red parabola to the vertex of my bridge parabola. And so I'm going to start by adjusting K, which moves it up or down. And it looks like that right there is about what I want. It looks like the H value is pretty much centered, and so now I'm just going to adjust the value of A. I know it has to be negative since we're pointing downward. And it looks like that's going to be our best value right there. And now it needs just a wee bit of a shift in the H direction, and that right there looks like about as good as we're going to get. Now we can see that that parabola on my graph matches the parabola of the bridge very, very well, and most importantly, I now have an equation from Desmos for this parabola on the bridge. And this again is the whole point of quadratic regression. It's just a technique where we can find an equation. So in this case, as we're looking at this, I can say the equation for the bridge parabola is going to be y equals negative 0.1 times x minus 0.1 minus 0.1. All of that has to be squared. Don't forget the squared value. And then my k value is 2, so I would say plus 2. And look at that. I now have an equation for the parabola that is that bridge. And that's what we're doing. That's our whole goal here. We're going to be wearing the Desmos tool out on this one because it is such a convenient way to do this. And so let's, without further ado, look at some of the problems that we're going to encounter here. So example 1 tells us we have a concentration in milligrams per liter of a medication in a patient's blood as time passes, and all of that's given in that table. So what we're supposed to do is we're supposed to find an equation to model that data and then tell whether or not that equation is a good fit. So in order to do this, we're going to use the regression feature of Desmos. This should look familiar to you. We did this for both linear and exponential functions, so now we're just doing it for quadratics. So the first thing you do, once you have this tool typed out or pulled up, and I will give you a link for it each time you need it, is that you take whatever data is in the table and enter that into your table in Desmos, and you can just type that in. So here's some good theater, watching a guy type in numbers. Woo! Try not to have too much fun here. And once we get all of those typed in, we'll kind of have a better idea of what's going on here. 84.4, 2, and 50.1, 2.5, and 15.6. There we go. Now, what's happened is Desmos has given us all the data that we need. Let me go ahead and get rid of this keypad here. Once we type this in, down here we'll automatically get the function. It doesn't make us do any work for that. And so let me zoom in a bit here. So now what we can see is the equation for our function, and I will scoot over here and write that in our notepad. So the equation I just copy down directly from Desmos. It gives it to me. No more work than that. I would say y equals, I don't need that 1 right there. That's just telling Desmos to look at the y values over here. And I don't need that tilde. That's just my my symbol to Desmos that I'm doing a regression. So I would say y equals the value of a, so negative 56.214, and let's round off to the thousandths place if nothing else is given, and then times x minus, and notice I don't need the x or the 1 on that x, and then the value of h is 1.2391. So I'll say 1.239, because again I can round to the thousandths place, squared, and then k is 95.663, so plus 95.663. And that's all there is to finding that equation, nothing harder than that. The more tricky part is this second question: is this equation a good fit? And for that, what we're going to look for is what's called the r-squared value. And the r-squared value tells us how good of a fit our data is. Just like for linear, where we had the r value, where the closer to 1 or negative 1 it was, the better the fit. For a quadratic, we have what's called the r-squared value. Now this is never going to be negative because it's squared, but the closer the r-squared value is to 1, the better the fit of the equation. So in this case, the r-squared value is 0.922, and the closer to 1 that is, the better. That's fairly close to 1, so we would say, yeah, this is a pretty good fit. It's not perfect, but it sure ain't bad. So the r-squared value, again, just tells us how good of a fit it is, and we want that to be closer to 1 for a really good fit. All right, next question we're going to look at is whether, or like using this to make predictions. So part B of this question asks, at what time will the patient have a maximum dose of medication in their bloodstream? So what I'm going to be looking for now is what is the maximum or y value of this function. Well, I have two ways of doing that. The first way is to kind of cheat a little bit and use the graph on Desmos. Notice that we can't see all of this function here, so I have a nice cheat way of doing that. So what we're going to do is this. Forgive me here. See if I can get what I just did erased. There we go. And what I'm going to do is go up here to the settings for Desmos, and then we want to adjust our settings for the x-axis and the y-axis. So for the x-axis, our smallest value is 0. So let's just go a little bit below that. We'll say negative 0.5, and our largest x value was 2.5. So let's kind of say 4. We'll just go a little bit bigger so that we can see that. On the y-axis, our lowest concentration was 0. So let's go with negative 1. To kind of give us some room there. Actually, you know what? Let's go a little bigger than that. Let's go negative 5. And then our biggest y value is going to be practically 100. So I'm going to say that. And now, once I've done that, once I've entered in this range on there, I can see that my function kind of pops up and is a little easier to read. So the question is, at what time will the patient have the maximum dose of medication in their bloodstream? Well, I can look at the graph and I can see that that maximum time is right about there. And in fact, if I scroll up on my graph a little bit, it'll give me that point. And so I can say that my time where they'll have the maximum medication is at 1.239 hours. So I'll say H equals 1.239 hours is when they have the maximum dose. Now, here's kind of a neat thing as well. That maximum is our vertex. So if we go back and we look at our equation, notice right here, this is the x-coordinate of our vertex, and notice that answer is the amount of time where the maximum is in there. So if you're clever, you can actually just get this from the equation, knowing that this is the x value, in this case time, for our maximum, and this will be the y value. So we know at 1.239 hours, a maximum concentration of 95.663 is reached. Notice that's less than this value here. This is why we have this r squared value telling us that this isn't exact. It's pretty good, but it's not exact. Alright, so there we go. We found our maximum. The next question is going to ask us how long will it take for the medication to be completely removed from the patient's bloodstream. So this question is asking us how long will it be until all of that's gone, that is until the concentration in their blood reaches 0 again. And so if we look at our graph, that's going to be the point at which this crosses the x-axis again. So here we can see that we reach a concentration of 0 after 2.544 hours. And so this x-intercept, this root, tells us where that is. So in this case, how long will it take? Well, it will take 2.544 hours for that medication to completely leave their bloodstream. Now you can kind of see inherently the usefulness of something like this for quadratic regression, specifically in this example, just by taking a few measurements, for instance, every half hour of the amount of medication in a patient's bloodstream. You can now use this to make predictions for the future. For instance, you know this patient will need another dose in 2.5 hours, or even farther than that. If you know you don't want the concentration to fall below, say, 20 milligrams per liter, you know that you're going to have to give this patient more medicine after about 2 hours or so. So this allows you to make really useful predictions, which is the whole point of regression. So to recap, regression is just used to find an equation. Once you've got the equation for the data, you can make predictions about it. That's the whole usefulness of this. And then the r-squared value tells you how well your equation fits the data. The closer to 1, the better.